Okay, and while Victoria prepares, we'll go with our second talk for today. This talk will be Victoria Peterson who will be presenting. So Victoria is a concept assistant researcher at the Institute of Applied Mathematics of Litoral in Santa Fe, and an associate professor at the Universidad Nacional del Litoral. She holds a biomedical engineering degree from the Universidad Nacional de Entre Ríos and a PhD degree in engineering from the Universidad Nacional del Litoral. She was a postdoc at the Brain Modulation Lab as a Harvard Research Fellow in the Massachusetts General Hospital in Boston. Currently, she serves as an international external collaborator for the Brain Modulation Lab. She has more than 10 years of experience working with machine learning solutions from brain signal decoding in the context of brain-computer interfaces. And one of her research projects was nominated to receive the BCA Award in 2021. And Victoria today will be talking about BCI.
Okay, so now I'm ready. So thank you very much, first of all, for being here. I know that it's a really complicated task. My brain is kind of squished, so I can imagine your brain is also. I'm going to do my best to keep you entertained as not to start date for that yesterday. Yeah. So my name is Victoria Peterson. I'm going to talk about machine learning for neural decoding in brain-computer interfaces. And before going to that, I want to introduce a little bit where I am. So I am a CONICET assistant researcher, and my institute is located at Santa Fe. Santa Fe is a province that is like I had to do this, that is like 500 kilometers towards the north from Buenos Aires. And there is a big pole of scientific and a beautiful community that lives in between university and this center. And from all of these buildings that you can see here, there is one, this is a beautiful one, this is the IMAL, Institute of Applied Mathematics from the Litoral, and this is where I work. And we have a beautiful landscape, you can see here from the nature, and something really great when you work until late in the evening, as I do sometimes, you can have this beautiful sunset there. And something really great is that we are a big group of people. We are like 14 researchers, and there are like 16 postdoc and PhD students there. Also among them, we can also say that we have 4 research assistants in total. So I lead the Applied Computational Neuroengineering Lab there. We call it NICA Lab. And initially were my advisor and I. Yeah. But now that there is a year since I started my position, we are a bunch of people. We have a research assistant, 1 PhD student, 1 master student, 1 undergraduate student, and 1 external collaborator. I have to start defining what a BCI is, right? Because maybe most of you don't know what that is, and it's okay, because that's the reason why I'm here. And going for the basic, I will tell you there are so many different definitions from BCI, and I'm going to only stick to the one that I like the most. That is, a BCI is a system that measures the brain activity of the central nervous system and transform it into artificial outputs. Those artificial outputs have the aim to replace, repair, improve, increase, or supply those neural outputs, right? And if you have inferred a brain-computer interfaces needed a brain, right? And something is really interesting, and I want to also to make a point here, is that we are now it's only 40 years from the first time that the BCI definition was given as a field, and that happened in a paper from the Vidal in the 1973. So this is a really kind of new area of discipline, and there is a really interesting how has been already growing a lot. So I told you we need a brain. So we need a brain, and we need to measure the brain activity of that brain. And I will focus on this talk on how we can measure the electrical brain activity of the brain. There are several ways of doing so, and one, and I will just talk about the one I use, and we can do that by using surface EEG that are actually connected to the scalp, or we can do some invasive recording in which we have electrocortical data being captured by these ECOG sensors that are called, or we can go a little bit deeper and use for example, some leads that are called leads, but we are having like the local field potential being captured for different substructure of the brain, like the SDN, the basal ganglia, so different places from the really subcortex area. So once we have decided how to measure the brain activity, we ended up having electrical brain activity. And that electrical brain activity is what the BCI wants to do, is to convert it into some control command, right? And we do that in the computer. After we have a control command, most probably we give to the patient or to the user some type of feedback. And now you maybe will asking like where the machine learning is. And it's all around. And I will tell you that these electrical brain activity are temporal series with all that convey, working with a temporal series. And that here, for having this beautiful control command and trying to give some outputs and feedback to the patient, we use a lot of machine learning, right? Okay, I will talk about some applications for how brain-computer interfaces can be used in health, because maybe you can imagine now, oh, I can do super cool stuff, like I have a new video game which I can control with my brain. Yes, you can do that. There are so many applications with BCI, but I'm gonna just focus in the health applications because it's what I'll do. And so I can ask any question regarding others. So I will talk about BCI for stroke rehab. I will talk about BCI for epilepsy treatment. And I will talk about BCI for Parkinson's disease treatment. And let's start for the very first one, that is for stroke rehab. So to make the story short, I want you to imagine that there is a patient that has had a stroke, and in like 30% of the patients, they live with some impaired limb, and most probably it's the upper limb. So they go to therapy. And we can think about an alternative type of therapy by using these BCI systems. For that, here, we are thinking that we have surface EEG, so no invasive EEG, and we are going to attach to the impaired hand some type of robotic or external device, like a hand exoskeleton, like here. So we are going to ask the patient, try to attempt to make the movement or think about making the movement. So because that's something that the patient can do, although the movement cannot be really done, right? Oh, that was not the case. So we have the brain activity, and this brain activity should be transformed into, is the patient trying to move? Yes, no. If that is the case, we are going to provide some feedback that can be like literally like the sensory feedback and literally seeing the hand being like moved. So we change from a desire to really execution of the movement. And we can give some meaningful feedback also in order to provide to the patient like, you're making it good, you need to do more, right? So the idea here is to develop something that is a closed loop, something that we can help the patient in how is the mental cognition, how is that I have to control this BCI, because that is hard. That is really hard. And on the other hand, there is machine learning that needs to adapt to these changes that are being happening in the brain of this person along the patient is also being training to use these systems. So I will start like the first goal in this project, because this is a huge project that we are ongoing working on. And the first one, like I want to talk here, is like how we can address the EEG variability across sessions of BCI, because EEG is a temporal series, and as such, it's really not a stationary signal. So whenever I have a model and I want my patient to use it, this is a therapy session, I want my patient to use this system like one day, the day after, maybe 2 weeks after, and that is something that we need to address and take into account. So if that is the case, most probably the system that you have trained, your beautiful machine learning model that is working so well in the data you capture from the first day is gonna fail in the second day, in the day after that, because data most probably have been changed. And in the best case scenario, this is a covariance shift problems, right? And if that is the case, we are really screwed, because if that we might need to capture more data. That means more time in the therapy session without feedback, and that is what we don't want. So I came with this idea after taking a Marco course in the summer school in machine learning in 2018. So the idea of okay, let's think about these problems as a domain adaptation problem. As such, we can use optimal transport for that. And although optimal transport sometimes is being used to this domain adaptation in which the training data is being adapted to fit the testing data, here we do the opposite because of the machine learning application we want. We do not want to spend a lot of time in capturing data for retraining a model. We don't want that. So for that, we came with this simple solution in which literally we have this we have these two domains, the source domain in which our classifier was trained, the testing domain in which the classifier one is going to be tested online, and we want to provide feedback really, really quickly. And we do the backward optimization. So we do the backward optimal transport, and we try to fit the distribution of the dating data so as to match the distribution of the training data, and we can use the same classifier that was trained the day before. That's the idea, simple idea. And to make the story short, you can then go into the paper, but we show that we can have huge improvement with respect to the other competitors. And not only that we are really having huge improvements, is that we do this without adding any delay in the feedback or the feedback time in which we can provide this. So this is so great. This paper has been published in 2022, and this project was nominated to receive the BCI award in 2021, so the year before. If you want, you will always see here the QR code. If everything is open source, so you can go to the GitHub and learn a little bit more. So happy to do that. Then there is a huge problem, and this is a project that is led by Catalina Galvan, my PhD student. So there is a huge problem when we work on this. So when we have this data, it's really small, the time at which we can capture this data, maybe 40 minutes, maybe less. So if we want to use deep learning, you can imagine that, you don't have enough data. So something that we need to do is come up with some ideas. And for that, we are using like a pipeline that is being thought to recreate artificial data, so simulated data, that looks like the real data. With that in hand, if we were able to provide kind of real data like a generative model, right? We can fit during training, we can make some augmentation strategies, right? So we can use this artificial data with combination with the real data, and we are showing here how some the improvements we can have. So also, you can go and see more in the repo. This is a paper that is also now under review. And then we decided to combine these two ideas into one, because optimal transport, this background formulation that we call BOTA, was so great. You have seen that. And we wanted to know if the success of that algorithm was only based on the algorithm itself, or there is something from the user, although it's like it makes no sense. So we combined what we knew regarding how optimal transport was working for that, and this data simulated by Catalina, this Python BCI, I didn't say the name. So in order to address this issue, a good patient is a good patient with respect to the attempt to making a movement is being evaluated by something that they call event-related desynchronization, right? It's something that happens in the brain that is my biomarker to know how good the patient is in making the attempt or the machination to make the movement. So in a beautiful life, when everything is kind of great, like 45% here, there is no gain in using optimal transport because the patient is so good in making it. But as long as that value is going down, going down, and going down, the person is trying to do it really, really hard, but maybe it's not the correct way. So here I show, for example, there is only a 10% of event-related synchronization. There is an attempt. The person is trying to do that, but maybe in not the correct percentage, right? Not the correct power. So optimal transport can help those users in order to say you are doing the correct class, you are trying to make the movement when I ask you to do that, but you know that, try harder. Next time, try harder. So this is the idea we are working on now. This is a really work in progress, and I hope to talk about this more next year, right? I hope. So second application is going to be BCI for epilepsy, for Parkinson's disease. And I tell you, this is was part of what I did for my postdoc in MGA at Harvard, and this was a great project that I was hired, in which it was a collaboration with Charité in Berlin, beautiful group there, in which what we wanted to do is try to build intelligent, adaptive brain stimulation systems. Deep brain stimulation system, which means that for Parkinson's disease patients, in the latest case in which they are really they have refractory to the drug like a treatment, they maybe can be a good candidate to go to the surgery. So they are implanted an electrode lead that is called the DBS lead in really subcortical areas of the brain that helps to remove or diminish the typical tremor, or movement or motor symptoms that we do know Parkinson's disease patient has. So what happens is that whenever the electrode is located, there are some electrical activity that is being delivered continuously, right? And that had a lot of, as you can imagine, side effects. In order to reduce those side effects, we can think about creating something that is intelligent and adapts whenever the patient wants to walk, want to talk, or maybe want to grab a glass of water, right? So we want to help the patient in doing that while avoiding the side effects that we can have. So the idea here is trying to do this. We work and we have so many great results, but I'm going to talk the last one, and that is the idea of how we can use all the electrodes, all the contact that I have, use it all of them together, gathering the spatial information in order to provide these features to the system. Because you may not know it, but this area is still using one single channel. And they looking for it, really out which is the best one, which is the best one. So here I say, okay, but you know what? When we are having actually EEG recordings, something that we can think about this, and maybe, you already inferred it, but something that the way we can think about this signal is they are like linear combination of sources. If you know about ICA, this looks like a model of ICA, or blind source separation. And literally it's like that. What we have in a sensor is actually linear combination of different sources that in most of the cases are coming from the brain, in the best case scenario. So with this idea, we built a pipeline that is able to use all the recording at the same time, regardless from where the electrode is located, either in the cortex or in the subcortex area. We gather all that information and we extract features and we fit a model, right? So we showed that although we were having a little low counting electrode, we were only having 6, 8, really low, but that was the data that we were having at that time. We showed that there is a huge potential of using this spatial filters method that use all the data from the space together with respect to the single approach that is kind of the gold standard in the area. And something really great about this method is that they are linear methods, so they are really interpretable. So from the neurophysiological point of view, we can give some insight to the neurosurgeon, for example, how is that the brain activity is being mapped when in the different areas of the brain. Last application is BCI for epilepsy treatment. And this is a beautiful thing. So when I was working in the US, there's something really unique that for epilepsy, resistant drug treatment patients, they are also good candidates to go and use this responsive neurostimulation system. That is the first FDA approval bidirectional BCI system, which means bidirectional, means that it senses and stimuli as a closed loop. And that is being used not as a research or an investigation site, it's actually being used in the clinic. That are patients being implanted with this, and they live with this like a normal life. There's a huge increment in the quality of life. So something that happened is that these patients are actually going to the RNS implantation. They go, then they had done some different visits to the clinic, because the reason why they go to the clinic is that there are some adjustments for the programming epoch parameters that are called, because maybe the way the treatment is is responsive. Maybe we need to adjust a little bit less or a little bit more the parameter at which the signals are being, defined. Like it's a sign, I don't know, I would say like it's a rectangular with this width, with this frequency, and blah, blah, blah. Those parameters are being, decided in how good I will say the counting of seizures of epileptic activity is being seen in the data. So the reason why I'm saying this is because these patients, every day of their life, they can upload or download, it depends on where you see it, their data. They literally use a bank, and this data is being, captured in this beautiful cloud, and which we now have for like a big amount of patients. We have data for years. I'm saying something that is incredibly high when we come from BCI system. Like we are having a lot of data for the same patient across a huge time of a period, which is great for a BCI system or a machine learner, but it's not great for recognition, because that means that that person is to view each one of these data and annotate, this is epileptic, this is not, which is super time consuming. So that's the reason why my boss told me, we need something intelligent. We need something, and we need something from the deep learning. So yeah, I came up with this kind of crazy architecture, like we call like ISPNet, that is invasive electrographic seizure pattern net, in which we do some convolutions, we do some like recurrent nets, everything that you already know. But something that we did like a really as a proxy is that since we wanted to know when, not only if there was a recording that has a seizure, but also when the seizure started, we did this kind of trick in which we convert the one hot encoding in a really continuous, smooth label, and we were able to like or to address or tackle these two tasks into one, which was really great in that sense. So we actually show this. Here I'm showing like how the net is performing in a lead one patient out scenario, like it's really mimicking like the clinic scenario, in which we see that the error time at which, on average, the system are like capturing the onset of the seizure is 3.6 seconds. For you, maybe it's like, okay, that looks a lot, but you can imagine that in between two radars, there are 5 seconds of like disagreement, so it's kind of a new radar. So that is something that for you to tune up the bundle. And also the accuracy that we were having here was 90 seconds. Okay, that's a balance accuracy problem. Something that also is important to show is like, since the RNS system is a bidirectional system, of course, it senses when there is epileptic activity. So the first question that you may have asked is like, why you're doing this? There is a system that is doing this all the time. And the reason why this is needed is because these systems are too sensitive. Yeah? So there is a need to really evaluate this. And we are doing this really offline, so there is no harm in using deep learning, right? Same here, like we were able to show like we are more precise on time, and that is important for like evaluating the outcome of these patients. Then we say how we can like actually, okay, this is great, but this is useful for maybe one cohort, one hospital data. We can use it for another hospital data. Yes, we can. We do some simple ensemble learning strategy, and we were able to like literally have for this new cohort of patients never seen, literally the perfect lead out testing data. We are actually showing here like this is from this new cohort of patients. This is for the patient we were having before. You may realize that the values are really in the same range. So we were able to make it across sites, I would say, intelligent system. So this is a paper that is actually now under review. I hope to have news really soon. And here the code. And okay, so now I hope you have realized that when we talk about BCI, we talk about a lot of stuff regarding machine learning, because I have just say a few, like transfer learning, domain adaptation, deep learning, ensemble learning, and statistical machine learning. And this is such some, because I just talk about these 3 applications. But to be honest, this is a really interdisciplinary area, and there is a lot to do, which is really beautiful, and that's why I like it really fast, because this really enriched environment. So with this, I'm gonna thank my collaborators, and this is my team. If you are interested, you can join us and follow us, and thank you.
Thank you, Victoria, for the amazing talk. So, yeah, question.
Thank you very much for the talk. Does it make any sense to combine the BCI approach with MRI images?
Yeah, but the problem there, so everyone has, heard that. So if there is any sense to combine BCI with MRI images, it makes a lot of sense. Actually, when we use a BCI or EEG data to understand like which are the sources, literally, solving the inverse problem, we go to the MRI images and try to make them match. Using all of them together, can be kind of problematic because MRI activity is really low temporal data, so it's different what can be captured, and maybe that can give a little bit delays in what you want to measure. And for the portability point of view, that will mean that maybe we can use as a proxy, but for the portability point of view, MRI images are not the great idea.
Any more questions? Otherwise, we move to the next speaker in the interest of time. Victoria will be also around here, so